and I think we'll just get rolling, Zeno. I think we'll just take it from here. So the great thing is, everyone, like I said, before we get into it, this is going to be recorded, so you're not going to be missing out on anything. I'll say the same thing later on. So when everyone is, I'm pretty sure in the next 10 or 15 minutes, we'll have more people in, but we'll just get things rocking. So welcome, everyone. Hello and welcome to Cave Academy. I'm your host, Ross Baxter, and today is the very first masterclass here at Cave. So thank you, everyone, for joining us here live. It's a pleasure to be here. The great thing here at Cave, we're in collaboration with VES London. So first things first, we want to thank VES London for all their support here at Cave. It's a pleasure to have them on. Most importantly, throughout the year, we're going to be hosting a series of masterclasses throughout the year, covering a variety of topics within the game and film industries. You name it, we're going to be diving into it, all the way from game design to kit bashing to today's main topic, cameras and lenses with Zeno Pelgrims. So like I said, today's guest is Zeno, and he's going to be diving into camera lenses. He's an incredibly talented artist and instructor. You name it, the man knows it all, shaders, lighting to render engines. And we're going to be, you just see the face, Zeno. Awesome. But yeah, most importantly, for Cave Academy, we want you to get involved. So for the second half of the masterclass, we're going to be hosting a Q&A. So like I said, this is your chance to ask questions. So like I said, make sure to select the Q&A section, ask your question, and most importantly, we don't want you to be afraid. Like, ask as many questions as you guys can, and Zeno and I will do our best to answer them. So first things first, Zeno, it's a pleasure having you here. Thanks for coming on, man.
Thanks for the invite. Yeah.
Anytime. I'm so excited. It's going to be so cool. There's so many great topics. But I guess we'll just keep it simple first. So good old introductions. Tell us a wee bit about yourself.
So basically, I'm a lead shading artist, right? Or surfacing. I think you're including the hair stuff.
Yep.
But I'm also a very big photography nerd. And that's it'll be the intersection today that we'll be talking about.
Perfect. Yeah, because like that was the thing. So I was talking to you this previously. So Zeno, he's made so many incredible art pieces, and he's worked in so many different fields, and he's worked on like things such as Netflix's Love, Death and Robots. He does freelance work to personal projects. So just to start off with a fun kind of topic before we get into today's presentation, I kind of just wanted to kind of put you on the spot. Do you have like a personal favorite project out of all these projects you've done over the years? I'm very intrigued to find out.
Yeah, I don't know how many of these people here know my work, but basically I once made this little piece called like Still Life.
Nice.
And I think I was at a great crossroads at a time. You know, when you learn more about 3D, basically improve your eye, right?
Yeah, of course.
And then after that, it gets harder to do good work in your mind. And I think I was at a perfect crossroads where I got an insane amount of satisfaction from doing it, because my eye wasn't, that great, but the render was okay. And yeah, I clearly, distinctly remember that being a great feeling. And so I think that, holds the most emotional value, at least.
Of course. Okay, dude, I'm so happy you said that, because like I was, when I was talking to you about this as well, like one of the favorite things about this Still Life piece, and also like I thought the Naughty Princess piece was great as well. It's your ability to create story, but most importantly, your ability to make us kind of feel it's always such alive when you see your artwork, and it's that ability and the power of shaders, the power of lighting, you name it. Like all these kind of topics we're going to be diving in today, that Zeno's going to be talking about. It's super important, and I think it's a field that we as artists, especially, well, for me anyway, when I was studying in university, this was kind of an area that wasn't really touched upon as much as we'd like to see. And I think that's the great thing about this masterclass, because it's going to really open things up for you, and it's great seeing everyone joining in. And I think we'll just take it from here. So Zeno, I shall pass the ropes over to you. So everyone, welcome. This is Camera Lenses with Zeno Pelgrims. Enjoy the show.
Well, thank you very much. Yeah, let's jump straight in, right? So,
perfect.
First, a bit about me. I'm a surfacing lead, but also a photography nerd. I specifically like to shoot these big, bulky, medium format analog, like old vintage cameras. And when I think of shooting photos, there's basically three components that we have to simulate, right? And first of all, there's all of the physics, or like the light physics that happens before we hit the lens, before a light ray hits the lens. And we've become pretty good at that in CG, I feel. Like lots of research, like doing pretty great. Then on the other side, we've got basically the photons interacting with the chemicals. And we're also making progress there, I feel. Like recently, for example, the ACES adoption is great, you know, like nice highlight roll-offs. It's all good to see. But in the middle, obviously, there's the lens. You know, it's a bunch of glass. And we've basically been using an old approximation for that. It's like from the 80s. And I feel like we can do better than that. So basically, I've been trying to do a little bit better than that. So I've been on a quest to make computer-generated images lose that kind of pixel perfectness, kind of introduce the glass in between. My camera is flying. Not sturdy at all. Great. So basically, a lot happens in between the space in between the space between the first object hit and your camera sensor. And this gets neglected, but we're used to seeing this, you know, in real photographs. So basically, I feel like we have an opportunity to make our renders more realistic, and not just your renders, like everyone's renders, which is pretty exciting, especially because today we're in this climate of like micro improvements to the quality of computer-generated images. And we're using this huge approximation. So yeah, I just feel like we can do better than that. It just needs a bunch of work put in. So there's many different types of camera shaders, like some of them that you might have already interacted with, some of them that you probably don't have interacted with yet. So first of all, we've got the pinhole. It's kind of like the most rudimentary type of camera shader. All of the rays start at the origin and then sort of spread out. There's no depth of field in this. And then in 1984, the thin lens got introduced, or at least the computer graphics implementation of the thin lens. And that allowed us to simulate depth of field, distributed ray tracing, that was called. And then in 1995, Kolb introduced naive ray tracing, or like not completely naive, because we know the order of the lens elements. So it's faster than regular ray tracing, like, you know, finding the intersections between all of these lenses. But it's kind of slow, to be honest. I tried implementing this myself and it's not ideal. So then polynomial optics got introduced a few years ago. Basically allows you to shoot a bunch of rays and then fit polynomials to these rays. And that basically allows transformation from the sensor position to your exit pupil in a very, very fast way. But the problem is that there's no zoom capabilities. So it's like fitted to a prime lens. More recently, there's been neural network based ones, but I haven't seen any adoption of those yet. So maybe it's up to you guys to change that. Then there's also a bunch of other types of camera shaders, like the orthographic one, the 360-degree one, etc. But today, we'll basically be talking about the thin lens and the pinhole one. So I'm not going to introduce anything groundbreaking today. I'm going to keep the mathematics very simple, and I really want to convey a kind of step-by-step approach to actually getting a render out with something that you compiled yourself. Because it's not the mathematics that's actually the biggest barrier at first. It's like you need to start writing C++, but it's not just C++ that you can follow a tutorial about. It sort of needs to slot into Arnold. And there's not a huge amount of documentation available about this. So yeah, let's try and clear that up. And I'll be skipping more technical explanations of programming concepts, because I don't feel like it's very, it doesn't add a lot to this presentation. But if you understand what the specific steps are, then you can just dive in each and every one yourself. You'll have to do that anyway. So if you understand the process, that's kind of what I want to convey today. So a few basics about camera shaders. Basically, it's one of the first computations on a ray that gets done, because it's at the start of the ray tree. fundamentally, they're really simple. So the good thing is that we only really need to compute two things, and that's the ray origin and the ray direction. So basically, where do we shoot a ray from, and where in the scene are we going to shoot it to? Of course, in the more complex camera models, this can get very complex, because obviously the origin then is on the exit pupil of your lens, and actually computing that can get complex. So to follow this, you'll actually need the Arnold SDK, or it's also called the API, in order to have some code or write some code and then have it communicate with the Arnold core. You don't need a license for this. You can just download it for free with this link. And then you'll definitely also need the API documentation. So let's have a quick look at that. If you are used to the regular Arnold documentation, this is very different. So it's basically documenting all of the C++ functionality. And if you first look at it, you're like, oh, dude, this, like, where do I go? Like, what does this all mean? But there's a structure to it. And I want to show you what kind of structure there is and how you can navigate it. So let's first start with the Arnold boilerplate. And what I mean by boilerplate is basically the templates that you have to fill in, code that always needs to be there in order to communicate with Arnold. These sections of code, they vary between different kinds of shaders. Not entirely, but they do vary. So for example, between a filter or a driver or a camera shader, they have different requirements, so it varies slightly. But for all camera shaders, no matter how complex, this is the same. So let's look at some code. So I've prepared this file. By the way, I'm linking everything at the end, so you can just download it from GitHub and get started with all of this. So basically, let's go over this one by one. So the first one is including the Arnold headers. It's simple, it just stays like this. Then this also just stays like this. I never ever change it, just rename this. It's by the metadata. Then we get to the pretty important bits, but I'll skip that for now because it makes sense later. But you can see that there's like sections like the node parameters. Of course, this in every single node, we need to define these, and it's pretty straightforward. All we need to do is put this like AI parameter float, then parameter name, the default. You have the different kind of function calls for booleans or for like vectors or etc. Then in the node initialization section, we're basically going to initialize the camera. So what that does is kind of create the camera data structure. For example, the random samplers are in there, that kind of stuff. We don't need to worry about this, just call it once. And then over here, this is pretty important. Basically, we're going to create a new data struct, which is this one. It's just like a sort of class or a struct that holds some internal variables. So it's a way that we can share data between these different sections. So for example, in the node initialization, I pretty much only do the setting up of the data container. And then in the node update section, we're basically going to do all of the computations that need to be done when the node is updated. So for example, the parameter changes. Important is that this is single threaded. So you can actually do some heavy pre-computation or something like that. And you don't need to worry about multi-threading. That all goes in here. So loading in the parameter values, maybe doing some one-time, singular time operations on those. And then the most important section, I would say, is the camera create ray section. So basically this gets called for every single camera ray that gets produced. So this needs to be fast as you can get it, or people will complain. Yeah, so in here, the most important part is that we set the origin and we set the direction. The camera shader at its most fundamental level only needs those two variables set for Arnold to work. Then in the node finish section, basically just clean up. So we're going to delete the data, this data container that we actually built. And then the node loaders, the camera reverse ray section, that's sort of more advanced, I would say. It's necessary to also provide a mapping from your scene to your sensor to be able to do screen space calculations, like adaptive subdivision, things like that. The good thing is, this can get very complex because you have a visual output, right? Like you simulate your lens effects in here, but it's actually okay to have some sort of crude approximation of where is this point in the scene going to be on your sensor in order to get measurements out. So for example, for the adaptive subdivision, it's not critical that it's an exact mapping. It just needs to be roughly approximate. So for example, in my polynomial optics implementation, I actually use a thin lens reverse because it's fast and it's all we need. So then in the node loader section, again, you just swap out, for example, the name of the node to something that you think is relevant. The rest kind of stays. So this is the template that we need to fill in to start doing interesting things. So then let's do some interesting things with it. So how do we actually model a camera through code? And it's actually pretty straightforward for the easier models. So over here, I've basically made a visualization that scatters some points on the sensor, and then translates them one focal length away. And if we then change the focal length, you basically get a sense of, oh, hey, small focal length will have a very wide field of view. Yeah. So basically, half a sensor height and one focal length away. Remember that, because we'll use that later. Great. So I think we can actually start writing some cool stuff. Instead of going through it all and writing it, blah, 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 I'm just going to comment things out and then go through it. So we don't spend too much time actually typing, and I can actually explain things. Great. Let's not worry about this concentric mapping for now, because we'll be introducing that with the thin lens. Currently, this is still like the pinhole camera that will do. So as you can see over here, basically created a bunch of variables that I want to share in between these sections. So for example, the sensor width, focal length, the f-stop. And I do this because I don't want to be querying the parameters every single time a rate gets created. I can do that once and just pass it through. So as you can see, I'm basically creating these parameters here. All are in centimeters at the moment, except for the f-stop, which is dimensionless. Over here, nothing changed. So in the initialization section, I'm still setting up the data structure, but there's no additional code there. And then over here, in the node update section, we can see that I'm actually starting to query these parameters. So for example, the sensor width, focus distance, and then I'm going to do some operations on that. I only need to be done once. So you have to split your code into sections. Like, do I need to calculate this every time? Or can I calculate it once and just reuse it? You always have to think about efficiency when writing stuff for path tracers, because yeah, people like it fast. So the aperture radius, we'll get back to that later. And we introduce the thin lens. So great. Right now, over here, we're basically creating a point with an add vector. So this is an Arnold type, and I'll show a little bit about that. So obviously, internally, Arnold uses a lot of vectors, right? And it basically opened up this API, this mathematics library, essentially, for everyone to use. So for example, in this add vector, you can always type it in here too, if you don't find something. Great. Just click on through if you don't find the actual thing. God damn it. I need the API section. Great. So you can see all of the functions that are kind of related to it, which ones you can use. But in this case, it's just essentially a basic mathematics library. And then over here, we see input. So if we want to figure out where this actually came from, we have to look at the camera create array section. So let's actually go and do that. This API gets you need to get a little bit experienced with it to start to know where things are. It's not immediately obvious, but it does make sense. Like, that's a great thing, it does make sense. So for example, in here, we've got this camera create array function. And we can actually see that it's being passed the node. So all of the information about the current node. Then some input data, and then some output data. And it's of this type. So add camera input. So if we click on that, you can actually see that we have some variables already available for us to use. For example, here we've got SX and SY, which are the screen space coordinates between -1 and 1. So if you want to use these, you can basically use the screen space coordinates and multiply that by half of our sensor width, because it ranges between -1 and 1. And then we're going to put the point one focal length away in the Z component. So basically the Z component is along the optical axis. Great. So if we then just create a direction from the center, so now we're going to normalize that. So the vector length is 1. And we're going to say output dot direction is direction from center. Great. So this will actually give us the correct array for a pinhole camera. But how do we compile this, right? We need to have a look at that. So let's jump into that first, because it needs to be done. Basically the way I do it. There's many different kinds of ways, and it's all about how to manage your compilation. But in the end, what gets passed to the compiler is just a line of code. So that's where we're going to jump to. Oops. Here we go. So basically, I'm compiling it for both Arnold 5 and 6, so we only need to worry about one of these lines. And essentially, over here, I am setting up some variables. It's pretty straightforward. So between OS X and Linux, there's different compilers. So I swap those out. For example, for OS X, it's Clang. For Linux, it's G++. Then I'm adding some compiler flags, which are these. So it's important that it's a shared library to have communicated with Arnold. The optimization level is important. And then we're basically going to include the Arnold header here. Then this is our file that we want to compile. And then we're going to basically say, hey, compile it to this file. So on Linux, for example, it will be a .so. On Windows, a .dll. On OS X, .dylib. And then we're also gonna supply the more Arnold stuff, basically. What actually it is, it's not so important at this point. The important thing is that you can just modify this. This is what I use for the most complicated camera shaders, right? And also for the most basic ones. So you just swap out these C++ files, and you can basically just save it as a make file, and then type make to compile it, and that's it. So I can see no compiler two compiler warnings because I don't have any code here, but no errors, so that's excellent. And then to render this, you either need to set an environment variable or something like that. But to do quick iterations like we actually need to do right now, I usually export an S file. And let's have a look at an S file here. And basically put the camera name. So we're going to define a node. Then I usually export a camera, just copy over the matrix, paste it in here. It's basically some like S file hacking that we do. But once we have set it up, it's pretty great and pretty straightforward. We can just change the parameters over here. So let's actually try and render this. So I've got the SDK in my home directory. Let's navigate to it. Can you guys see this, or should I make it bigger? Yeah, there we go. So Arnold 5.3, let's say, then kick. So great, we can see that we can use kick. They're gonna supply it an input file, which is called tests head on a platter. You'll see why that is called like that. Great, so let's try and execute this. And it says, oh, great, no camera found, because we didn't actually set an environment variable, we didn't put anything in the correct folders, but we can simply fix it on the command line by just saying -L, and then I'm going to navigate to where I compiled these files to, so that would be 5.3, and that should actually find it. So it's actually just the directory that these compiled files have gone into. You can see, well, hey, excellent. So we've got a head on a platter, no depth of field at all. Let's add some depth of field because this is like as basic as it gets. Great. As you can see, I can actually already start changing the focal length, for example, if I want to. Oops. And then just re-render. Much wider because I changed the focal length. Great. So let's forget about this for a second. Now to introduce some depth of field and actually implement the thin lens model. So what we basically need to do is compute a point on the focus plane. So for example, if your focus distance is 100 centimeters away, we need to calculate where this point ends up on that focus plane. So let's try and do that. First of all, we normalize our vector. And as you can see, you can change the focal length like this. Then we basically need to scale it to the focal plane. So the focal plane would be around here. You can change your focus distance to do that. And the point gets transformed there. And then the crucial step is to add some randomness, stochasticness to it. So what we're then going to do is translate the origin up to another point. And this will simulate the aperture. And this is actually where the depth of field comes from. Like right now, this actually acts as the lens. So let's actually show the mathematics about this. So basically, let's say we have a sensor. Now over here, we've got our optical axis. Let's say we shoot a ray. I'm not gonna do that. Let's say we shoot a ray. Great, because this is normalized, quite likely this will be 1. And since it has some perturbation, this will likely be something like 0.8. Great, so let's say we have the focus plane somewhere over here. And what we need to do is find the point on the focus plane. Ah, wow, this is annoying. Great. Basically, it would have been derailed like that. So great. So how do we actually do this, right? We've got the Z component of this array over here, and we need to find how many times it fits into here. So basically, we're going to ask how many times does this fit here? And we can simply do that by basically taking the absolute value of the focus distance over, so this is, let's say, d dot z. That's it. There's not much else that we need to do. And then to actually simulate the depth of field, like we saw earlier, we're going to pick a point on the unit disk and then scale it by the aperture radius. So let's say we end up with a point over here. And to simulate the depth of field, what we need to do, basically create an array like that. That's all. So let's do that. Great. So remember that I said that we'll actually first start with taking points on the unit disk. So we need to generate points with the most even distribution possible on the unit disk. But the most random number generators, or all random number generators, basically produce points between 0 and 1 on the unit square. So we actually need a way to transform the unit square to a disk. And this is what we're going to do with this function. It's pretty complicated. There's lots of pi's, like half pi's, quarter pi's, but we don't need to know the internals of this. Basically, you need to know that it transforms the unit square to a unit disk in a good way. So a little visualization is doing it like this. Basically, it pulls in those corners, and we'll end up with a pleasing distribution of points on the unit disk instead. Great. So first of all, we create a two-dimensional vector of the type that Arnold provides. We'll call it unit disk. And basically what we're going to do is input the lens coordinates. So we're lucky, and Arnold actually provides a really fast random number generator. And it already pre-computes these two numbers that we actually need per array for us. So let's use these. And again, if you're not sure what other information that there is that you can use, go to the API, and this is it. Like, there's not much in camera shaders, but we've got the screen space coordinates and then the lens coordinates, and we've got time for motion blur, and then we've got the derivatives for more important or like more complicated stuff. So then we're simply gonna create another point and scale it by the aperture radius. So the aperture radius, it's a pretty simple equation. It's just the focal length over 2 times the f-stop. And then you get the aperture radius in whatever units the focal length was. So we're gonna scale the unit disk. So between 0, or now it's between -1 and 1. That's actually due to some remapping in here. So we're going to scale that by the aperture radius to get our point on the lens. And then we're going to put the origin as our position on the lens. So it's basically exactly what we did here by translating it up with the aperture radius. See how we're making a new point. Then over here, we need to compute the focus plane intersection. So that's basically what we did over here. How many times does this fit in the focal distance? So the ray, how many times does the z component fit in the focal distance? Because then we can basically scale this multiplied ray by this amount to reach this point. So the goal is to compute this point on the focus plane. And simply enough, just the absolute value of the focus distance over the z component gets us a scalar value, right? And then we need to scale this direction from center. Again, that is this ray to the focus plane. Then we have that point, right? And then we still need to create a ray from our new point on the lens, which is scaled by the aperture radius. So we're basically going to normalize and then create a vector between 2 points by basic subtraction. It's important that you normalize a ray or your direction ray in Arnold because it assumes this. For example, I think your ray marching steps in volumes, etc., will be off. It basically assumes this because if you can do it in a smart way, you might be able to avoid the normalization, etc., etc. So that's basically it. Let's try and compile this and see if we actually have some depth of field. So we already have our setup over here where we have the f-stop. We've got the focal length, our sensor width has a physical value, and we're focusing at 45 centimeters. So let's recompile this by simply running make again. And then we're simply going to run this again. Oops. And we see that we have depth of field. So that's sort of like the most basic minimalist setup that you can get. You can continue building on top of this, but this is as basic as it gets. So let's jump back into the presentation. So basically, I want to leave you guys with some simple, some more complex, some really, really, really complex problems to try and solve if you want to start tackling camera shaders. First of all, or not first, but I think it would be great to find an analytical optical vignetting. So currently the way that this works is we basically create a second aperture and then we do an intersection test on that aperture plane. And if that happens to be outside of that virtual aperture radius, then we just call it, create a new random number and try again. But we can probably be smarter about this. Yeah, it's sort of an open problem, I consider. Then implementing astigmatism, coma, all of the side elaborations would be great. So I know Octane has done that recently, which is great. But you can do this too. So all you need to do to solve this is just perturb your ray in a specific way by studying the like how these aberrations work. So it's just about a slight perturbation of this direction vector, and that will actually get you all of the or like the individual aberrations. So let's try and model this. You know, it makes for more interesting images. So why not? Chromatic aberration is still really tricky in Arnold because we can only fire one ray per screen space sample. So it's not, yeah, that probably is not a great one to solve, but that's kind of like the one that everyone wants to solve. Just saying, not so easy. And if you want to have a deep down dive, like zooms in the polynomial optics model, yes, please. That would actually open up a huge amount of possibilities. So there's at the moment not enough people working on this. I think there's a lot of improvements that we can make, and yeah, like I think you should join me. So all of the code is available there. You should be able to just you have to install the prerequisite things, like, for example, make. You need a C++ compiler, but those are things that you can just Google on how to do. And yeah, then just compile the make file and you're good to go. Like, just follow what I did right now. I'm also adding some more, how do I say it? Complex pieces of code that are related to cameras, specifically for Arnold. Marc-Antoine Desjardins is the guy that I took a lot of inspiration from when I started out and figured, kind of started going with this. And then, for example, my old naive ray tracing implementation, it still has a lot of goodies in there on how to do certain things, like optical vignetting, or fully ray tracing a camera, things like that. So that's basically it from me. Yeah, I would love to answer questions from everyone. So, Ross, can you take over?
Perfect. Everyone can see me again. That was an amazing presentation, Zeno. Like, I learned such a tremendous amount. It's great, great having you here once again. So, like I said, everyone who's here, join us here in the presentation here at Cave. If you guys have questions, so we've got questions rolling in. It's great seeing them. So as always, this is your chance to ask as many questions as possible. We've got the time, and at the end of the day, like I said right at the start, we don't want you to be afraid. So get those questions rolling. Is there maybe something that you want as to tackle that's a bit more particular in regards to the presentation? Maybe he wants to go over something, it'd be great. That's also available to you guys as well. But we'll start things off. So the first question is from Mohammed. He says, what are the benefits of accurate cameras in CG versus faking it in 2D posts? Zeno.
There's good reasons for both, I think, right? 2D posts, yeah, it's nice to be able to change things when the director says, it's too much or something like that.
Yeah.
But like doing it in CG, or like on the path tracer side, you get pixel perfect simulations essentially. And you don't need to, I've tried to implement more advanced camera models in Nuke, and what you end up dealing with are artifacts. And it's much nicer to worry about the correctness of mathematics rather than like pixel artifacts. So I think we just need to make this fast enough so we can just simulate the whole camera. And also, if we want to simulate more complex cameras, basically, if the you'll start getting like occlusion issues and stuff like that. If the aperture is big enough, then you actually see the scene from different points, and yeah, it just ends up being fixing pixel issues, and it's not my kind of thing. Obviously, it's been done to a great extent, but
of course, yeah. Thank you, awesome. So keep the questions rolling. We've got a lot of them coming through. It's great seeing everyone getting these questions through. So the next one, to add to CG cameras, how much to affect the LPES and data sensitive layers like depth NP? It's the second one up top there. I'm pretty sure you'll see it on your screen as well, Zeno.
Yeah,
that's from Mohammed.
Yeah, I basically, I think you say if you add these kind of shaders, how are these AOVs affected, right? They just work, because Arnold basically does these same calculations at the start of the ray tree. Just we are going to modify these calculations a little bit, and yeah, it just works.
Perfect. Next one we've got is great talk. Do you guys have any good resources for understanding the maths, physics behind lenses, especially with regards to modeling field curvature, as you mentioned in the presentation?
Yeah, so yeah, like I can send you some links actually. Maybe shoot me an email, and I'm very happy to send you some really great diagrams on how these aberrations work. By the way, field curvature is just a combination of tangential and sagittangential astigmatism. So field curvature by modeling by itself is actually really easy. Let me just try and show you how you actually do that. Remember how we over here scale it back to the focal plane or the focus plane, right? If we just scale these vectors without like normalized, we actually simulate field curvature. So it's actually omitting a term. So in code, it would basically look like this. Boom, field curvature. I do think it would be nicer to simulate this as the combination of the two types of astigmatism. But that's also totally possible. So yeah.
Perfect. They keep playing it. It's great. Awesome. So just so you know, everyone, if you just joined us late as well, I know there's some questions in the chat as well. Just make sure to put it in the Q&A, but I'll ask one of them from the chat. So one of the questions was, have you tried simulating spherical aberration instead of chromatic that is present in much older lenses?
Yeah, totally. Spherical aberration, we actually have a cool trick for. We can basically add a bias to this concentric disk mapping, and then we basically are able to simulate that in a very straightforward way. But again, it's just another aberration. So if you say, okay, for example, spherical aberration, I think it's only affected by the height of your aperture. So for example, rays that have a steeper angle, you're going to perturb those a little bit more. So the focus distance just shifts a little bit before, and then you end up simulating spherical aberration. It's pretty straightforward, and it's actually a great one to start to try and do as a beginner.
Yeah. Well, like, speaking of just beginners, I guess that's actually one of the questions I was going to ask you as well. Like, I know obviously you've dived into it when it comes to the presentation side of things, but when it comes to people, I guess, who aren't very technical heavy, or they're very new to, I guess, the mathematics side of things, is there anything that's like, where did you start everything? Was there like a main thing that got you started for that side of things?
No, I just wanted to solve a problem, and I kind of bit my teeth into it and struggled. I hope it's not that difficult for other people right now, but for me, it was. I basically wanted to implement depth of field and optical vignetting. Those were the first ones. Then I implemented image-based bogeys. I really got a lot of help from that guy called Marc-Antoine Desjardins. Taught me a lot about statistics and stuff like that. You need to construct probability density functions from your pixel values. It gets pretty complex after a bit, but luckily these are techniques that are very translatable to other parts of render engines. For example, hey, it's actually the same as when you have an HDRI and you need to sample the bright highlights much more than the areas that don't really affect your lighting so much.
Yeah.
So yeah, it sort of translates. But again, if you're stuck with anything, I'm very glad to answer a lot of these questions in more detail. So
perfect. Yeah, because at the end of the day, that's the great thing about Q&A, because like this is your chance, like I said, just keep them coming. And when it came to what Zeno was saying there about like Luke Dev scenes, etc., you name it, Jahiro as well, he also has his own Luke Dev setup, so you can check that out as well. And that's on the website when the website goes live, which we'll be talking about later on as well. Next questions, let's see. Joe says, awesome, cheers. Thank you, Joe. Much appreciated. Great seeing everyone enjoying the presentation. So let's go that one. Perfect. Okay, this is a big one. So I recently read that Framestore changed their renderer to in-house tool Freak. Before they also were using Arnold and wrote their own shaders for materials, volumes, etc. How does those shaders are different, like the standard surface or volume shaders from vanilla Arnold? That's the first one. It's the second one at the top. It's quite a big question, but great question. Thank you so much for asking.
So basically, I think what it's trying to ask is, what are the advantages of writing custom shaders over the already provided ones? That's just when you run into an issue that you can't solve, and you think, hey, like actually I've got the tools for that to solve it with a bit of code. Then yeah, you end up writing a custom shader.
Yeah.
It's always a journey because there's almost never examples of it, but yeah.
It's always the case. It's always the joys. It's all part of the learning curve.
Yeah.
Also, speaking of that question, so there's a second part as well, Zeno. So in the documentation of Arnold, it says that most materials could be done with the standard shader. What would be the advantages to write custom shaders?
Yeah. So again, it really depends on what you're asked to do or what you want to do yourself. If you can't do it with the standard tools, write your own. That's sort of the ideology.
I think that's the great thing about having you here as well today, is the fact that there's a whole world of technical that I guess, like I said right at the start, like we weren't really introduced to it at the start of our education, you name it. Obviously, it depends on the education you go to. And there's so many advantages to using shaders and understanding cameras that we can really learn from and make our scenes look more believable. So whether it's understanding look devs, you name it, whatever it may be. So next question. What have I missed? What would be the road to simulate the bokeh? Hopefully I'm pronouncing it right. The bokeh and the ratio stretch for an anamorphic shot. I love these. I'm learning so much here. This is great.
Let me show you. So for example, let's say we have this case over here, right? We can do anamorphic bokeh by actually simulating light through anamorphic lenses, right, which have cylindrical components. But a cheap way to do it is to just take this unit disk, and let's write a bit of backsalient over here. Let's say we just say the position of this.
I don't suppose you could zoom in a wee bit at all. Is that possible, Zeno?
I don't think so over here.
It's okay.
But basically, what we're going to do is just like scale the X component of this unit disk to. That's the main way that this is simulated at the moment. And then I think we can actually do better by doing some kind of interpolation there to create more anamorphic feeling shapes. But I would also recommend you to try and do a naive ray tracing implementation, because there's lots of anamorphic lens patents online, and yeah, like it's possible. This is the easy way, that's the difficult way.
Perfect. Next question. Once again, Mohammed, great. It's awesome seeing all the questions you've been asking. Like I said, just keep them firing through. So the question is, would lens flares ever be possible in a camera shader, perhaps with its own dedicated light path expression?
Yeah, so that's actually slightly more complex, because in Arnold we have a certain limitation that we can basically loop over all of the pixels, right?
Yep.
And with a lens flare, you actually have to start from the lens, which would be fine, right? But then it scatters light through the lens and scatters it onto many pixels. And there's actually no way to accumulate these values at a moment. Could change. I hope it will change. But that is sort of the basic infrastructure that is needed. If you do want to do lens simulation, there's actually an older polynomial optics implementation. I think it was done in 2014. And it's an out-of-the-box, basically, lens flare simulator, really fast and really high quality, full light transport through lenses.
Nice. Awesome. And like I said, folks, all this will be getting recorded once again. So if you guys miss anything as Zeno was discussing, make sure to check it out. Right, let's see who we've got next. Arvid's asking, how is the core team support on custom shader writing?
Yeah, pretty good. If you ask an interesting question, you do get a great response usually. I'm not quite sure if that counts for everyone, but these guys, they've always been willing to help me out pretty significantly. But you do need to ask specific questions, because if you just ask, hey, how do I do this, then it doesn't quite work that way.
Of course. Just like speaking, by the way, obviously when you're doing the presentation, and obviously today's main topic is Arnold, when I've talked to you previously about this before, so obviously I use V-Ray, etc. And speaking of the topic of like transferable, just when it comes to this, being able to use for other render engines, etc. How, like, I understand obviously a lot of it does apply to other cameras, etc. Like, what's your kind of thoughts on that?
Yeah, so the great thing is that the mathematics of path tracing or light transport is the same, you know, in every render. They might try and cut corners in their own special ways and kind of brand it as their own.
Yeah, of course.
The physics is the same, so it transfers like straight up.
Awesome, because like
but there's a slight problem, which is the APIs are different, right? It's written in a different way, so you have to get used to the new API. Maybe they supply some other types of information that you can use, but then not the types of information that you actually need. It depends.
Thanks for that. Of course. Well, that's super important. Like, at the end of the day, like, we all use different software, and obviously we can learn bits and bobs from each part of the presentation. And the fact that you say it is transferable just makes it so much easier for us. Next question from Peter. He says, is it possible to add color filtering / manipulation into the camera, lens, and shader? If so, how?
Yes, there is. So let me just show you a way. So we haven't really looked at the output sections of the camera nodes here. Oops, camera nodes. So inputs we looked at, output we didn't yet. And this is where the origin and the direction, but also a weighting is. So this is an RGB weighting. By default, it's set to 111. But if you say 011, then all of your rays will, you know, like the red channel. So you can actually manipulate this. Unfortunately, this is not enough to do chromatic aberration because you only end up darkening in this sense. To implement chromatic aberration, you'd like to send 3 rays, but we can only send 1 at the moment. So yeah, you can do color manipulation for sure.
Nice. Right, next one. So Bruce says, awesome session. Cheers. Great to see, Bruce, that you're enjoying it. Once again, folks, just keep them coming. So he says, obviously performance versus simulating, absolute realism will always be a trade-off with nuanced returns. Is there anything that you see as always easier in post?
It's a loaded question, I would say. There's an always in there, and this fast changing industry, I'm not quite sure if I want to place bets on that. I would like there to be nothing at all to be easier in post. Maybe draw overs, but that's just my mindset. More 2D focused people will feel different about that, and obviously they will see benefits that way.
Sweet.
But I think we should try and put everything into the light simulator and make it as fast as possible. There's still a lot to be done, I think. So,
like, that's like one of the great things as well of Arnold, especially. So I've only touched on it briefly, and this is why it's amazing having you here. But when I did start using Arnold, I found it a lot more intuitive, or at least it wasn't so technical heavy, if you know what I mean. Like, there was room for error in regards to the render itself. Like, there wasn't too much going on. Obviously, like, there's lots of nooks and crannies that makes rendering way better, making the final result a better product. But when it comes to actually learning it, there's so much to it. Next question we've got is the Arnold GPU API the same? And also, could these trainers run over Arnold GPU?
Great question. At a current moment in time, which is the 27th of April 2020, there's no support for GPU plugins yet.
Okay.
OSL support got introduced, but nothing on the GPU yet. So that part of their API is still private to them, probably because it's not finished enough to share with the world. But they will change for sure, no doubt.
Something to look forward to. Can't wait. Right. Next one is from Anton. He says, to piggyback on filtering, can one simulate camera diffusion in the renderers, such as black, pro, mist, classic fog, etc.
Yeah, so I've actually been working on something that's very similar to this. Some of you might have heard I'm working on a bidirectional camera shader. And basically, the one component is a camera shader. The other component, which does all the bidirectional tracing, is in a custom driver. So there's a filtering and the EXR output at the moment. There you can do it. In a camera shader, you cannot, because you'll need the, maybe if you perturb the rays in the right way, that you might be able to fake it. But like the classical kind of like ProMist or like those type of effects, no, that's not possible. Even not in a filter, because you can only write to the current pixel. And with these kind of things, it kind of splats, and you need to be able to write outside of the current bucket. And that's not, but maybe that will change. I've got a feeling that will change.
Fingers crossed. So next one, so we've got 2 still left. Like I said, right at the start, just keep them coming, and we'll see what we can do. So the next one is from Benjamin. He says, I have some experience with JavaScript and Houdini VX coding. Do you have a good resource for getting up to speed with the necessary amount of C++ to start dabbling into custom shaders?
I think if you already have the experience with JavaScript and Vex, you're in a good place, all right? Just like you had to learn Vex from JavaScript, it will apply. I would just look at examples. So for example, in this shader library, there's lots of shaders. These are really old. They're probably like 5 years old.
Okay.
It shows you how someone else does it, and that's the way I have learned, just by looking at examples. And obviously just writing C++ works in there. You just need to know which inputs you have and then which outputs you need to write. Everything else in between is just classical C++.
Right. Next one coming through. So is it possible to adjust the DOF after render, similar like Lightro, DSLR, like a deep like render? I know, a crazy question.
Yeah, so there are some roots to that, but they're all very complex.
There's a lot to it.
it would basically involve writing this type of camera shader in Nuke, for example, operating on deep data. And it would be sort of limited in how far you can adjust things, but it's the deep data that will do it for you. So it is possible, but it's complex.
Yeah.
And I don't know if it's worth it. I'm not actually sure. Yeah.
No, I understand. Thanks for saying that. Like when it comes to, I guess, like the questions as well, there's one thing I was wanting to ask, just in general, in terms of an artist perspective. Is there, I know you've touched on it so far, so obviously like, there's the main elements that makes a render better in regards to the camera settings, you name it. But when it comes to, I guess, more of like focusing on the art side of things, is there anything in particular you think artists are missing out on that are not, like, how can I say, like they're not maybe bring it to the next level? Obviously you've got vignetting, you've got all these things that you've talked about. Like when it comes to their final renders, what are they kind of missing? Because I know you focus so much on the observation, like the detail side of things.
Yeah, but it's completely not technical, I would say. Something that I often miss is applying the same concepts that you learn in lighting, right? Introducing gradients to lead your eye and things like that. And in art, like in any path tracer, it's very easy to just use a bunch of procedurals. And by using these, procedurals, we sometimes lose some of like those concepts of, hey, we need to lead the eye. And think about those types of things that we learned about in lighting. So it's, I would say focus on that, and then the technical side second.
Awesome answer. Thank you. That's great.
Technical side.
It's always a hard one because rendering, like if you're new to it, for example, like if you literally just joined in today's presentation, obviously there's a lot to it. There's a lot of things going on. And obviously when it comes to making a final image, whether it's composition, you name it, whatever it may be, there's a lot a lot to making a good image, and it's getting that right balance between artistic versus technical. And I think when it comes to the point that we discussed right at the start of the presentation, is the theory. Like theory is like the end on. It's like it's the maker or breaker. Like if put the time into the theory, actually understand what's going on, because it was the theory for me that really helped me grow as an artist, and not just going into shaders and just like sliding everything. As cliche as that may be, it's like actually understanding everything and giving reason instead of just forcing it. You know what I mean?
Yeah.
Perfect. So we're seeing lots of more cameras. Gee, was it? Everyone just like Ted, just like so many keep in. Right. Okay. Next one. Not about cameras, but will we be getting shaders.xyz back?
You can't have best of both. Basically, I only have so much time in a day, and I basically had this idea to create this bidirectional camera shader, which speeds things up significantly, like 30 times or something. It's pretty cool. And that took all of my time away. So will it ever come back? No, I don't think so. I don't think I have it in me to do another relaunch of it. That kind of happened twice, and I don't think I can do it a third time. But if anyone else makes it, I would like to join.
Yeah. Take over the ranks. Take over the role. Why not?
Yeah.
But I'll be saying as well at the end, you guys can find Zeno on his website, zenopelgrims.com. So make sure to check it out. So at zenopelgrims.com if you're wanting to check out his work. Right, let's see what we've got next. Next question is, okay, we've done that one. Make sure we get that one through. Right, Timothy says, can you show us some great examples made with your custom camera shaders? And did you use them on some actual production?
I think all of the people that are still right here right now deserve some kind of preview, right? So let's try and see if we can find anything.
Perfect.
The website is actually already online, but don't tell anyone. Oops. Anyway, so basically, this is, I don't know what the compression does to this, but this is unidirectional, this is bidirectional, the same for the polynomial optics model. It's just a lot faster. And there are some available lens models in here. Let me just scale this down a bit. Essentially all of these renders, they're with full lens simulation. So for example, over here, this is like an old Petzval lens from the 1900s. This actually has some, like a bokeh image attached to add some naturalness to it. One of my personal favorites is this one. It's like, no, this one. Look at the complexity of that. I love that. So it's like some unknown Canon lens that I found in a lens spade.
Yeah.
But yeah, we can simulate this right now. We just need to do it in a fast way. Sort of the crux. Yeah.
Perfect. Okay, so next one. Tane says, hi, great presentation. Thank you so much. I'm glad you're enjoying it. Just wondering if it would be a good idea to have some controls, some controls to simulate or avoid more effects while rendering. Basically give some sort of control for it. I remember facing some issues a while back, but at that time, rendering a higher resolution image seemed to be the only solution. Do you think the neutral network powered camera shaders could be of use here?
I don't think so. Like moire effects are a fundamental problem in statistics, essentially. Like in our path tracing algorithms, it all has to do with the rate of sampling compared to your function. And sometimes the function actually, it doesn't, I don't know how to explain this properly right now, but the answer is no.
Okay.
So that wouldn't be possible from within a camera shader. That's actually the filtering that takes care of that usually. It introduces blurring. It's an unsolved problem for sure.
Yeah. Still trying to figure it out. Okay. So we've got one more question. Let's see. So caustics bidirectional. You want to give it a go? That's the question by Arvid.
Yeah, so caustics. That's an interesting one. The bidirectional component that I've written is just for camera shaders. So just for camera rays more specifically. So it doesn't affect any other part of the scene. It's just high powering the camera rays to be able to make lens rendering faster. So probably not. Sorry, Arvid.
Right, folks, if you guys have any more questions,
email me.
Yeah, you can even reach out to him. Make sure to send him a message. Like, that's an opportunity. When someone says that is an opportunity in a lifetime, because at the end of the day, reaching out to your artists that you're inspired by, you name it, it's a great opportunity. Make the most of that. Do you also use LinkedIn at all by any chance, or is email always your best choice of contact?
Email, yeah. Don't really use LinkedIn. Yeah.
Perfect. But yeah, if that's the end of the questions, I'll wait a few more minutes just to make sure. There's plenty of time. It's completely up to you guys. If you guys have any more questions out of the day, this is your chance to ask away. And if not, we will take it from there. But first things first, Zeno, I just want to say it's been a pleasure having you on. Thank you so much for joining us here at Cave. It's awesome. Just such an incredible presentation. Everything you broke down. I learned so much. It's crazy how much I learned myself just by tuning in and watching. People are saying thank you. Great to see everyone enjoying it. But yeah, thank you everyone for joining us here today. Also, don't forget the masterclasses are recorded. So if you joined us late or want to go back and see a specific part, you can do so. So that'll be on the website. Just remember, the website won't be going live until the end of this week. So make sure to tune in for that. That's www.caveacademy.com. And also, when it comes to these masterclasses, like I said, these are free, and we've got many guests to come. Our next masterclass is actually on Thursday the 7th. We've got an incredible guest. We have Mac Moore coming on from Conductor, who will be giving you a presentation about their cloud rendering service. So once again, thank you everyone. It's been a pleasure. And thanks once again to VS London for collaborating with us here at Cave. Make sure to check them out. And we will see you guys in the next master. Oh, a question literally just came at the last second. Perfect. I'll be nice. We'll answer this one. So Matthias says, when will the camera shaders you just teased be released?
I can't say yet, unfortunately. And I'm going to be totally honest about it. Yep. It's because I'm waiting for some adjustment in the Arnold API. And perfect. When that will come through, we'll actually be able to use some of these new features that might or might not come.
Yep.
And then it'll be twice as good. So it's worth waiting for.
Perfect, everyone. So once again, thank you for joining us, and we will see you guys in the next masterclass. Bye for now.
Ciao, guys.
See you guys later. Yeah. Bye-bye.